So we load the Ciara dataset. It's one of the sample datasets. It's for Brazil, and it has a bunch of socioeconomic indicators, as well as measures of the presence of Zika and microcephaly, which are both diseases spread by mosquitoes. What I'm going to do first is go over some classic thematic maps, quantile map, equal intervals map, and natural breaks map. So those are kind of standard. Most software has these. Then I'm going to go over some statistical maps, which add a little more intelligence, so to speak, to the maps. And I'll then get specific to GeoDa with the map toolbar and the different options that you have. And then if I have time, otherwise I'll do it next week, I'll talk about a co-location map, which is pretty unique to GeoDa, at least at this point. So the mapping functionality, you can invoke it by going to the map menu, and then it shows all the different kind of maps that you can make, or to this mapping icon, maps and rates, it says. And we're going to start with a quantile map, and we pick 5 categories. So you go down, pick 5, and then we're going to pick the variable housing. So here's housing. Go down a little bit. So this is a technically called a quintile map. It has 5 categories. How do you get these? You take the variable, and let's do that. We go to the table, and here's the table. We go to the variable housing. We've already seen this when we talked about the table. You click on this to have the ordering, and now they're ordered from small to large. Okay. What a quantile map does is it takes this ranking and then cuts it into equal parts. So each grouping, each bin, each classification has the same number of observations. Okay. The number of observations in each category is given here in parentheses. Is it the same? No. Why not? Okay. And this is one of the drawbacks of a quantile map, and also yet another way to illustrate the difference between spatial analysis and non-spatial analysis. So what I've got to do, and we did this already, I believe, is I'm going to create a new variable with the rank of the housing variables as they're sorted right now. So we go to the table, we go to the calculator, we're adding a variable. I'm calling it rank housing, and it's going to be integer because it's just a rank. And I'm going to put it right next to the housing variable. So I'm going to put it in front to the left of sanitation. Okay. So that will create an empty column right next to housing. There we go. Now we're going to go to the calculator again. We're going back to the calculator. We're going to Spatial, first tab. And then if we go down here, we've done this once before. We take enumerate, right? And so the moment I select this, the moment I click apply, then in this empty column here, the ranks will appear. Right? So apply, we have the ranks. Roughly, there should be 37 observations in each of these categories. The third group should start at 75. We can select each of these groups by clicking on the little rectangle. So if I click on the middle rectangle, it selects, it highlights the locations on the map. We've done selection before with the selection tool. This is another way of doing selection, where you select on the category in the map. The selected observations will be highlighted in the table, we know that. So we keep going down and there we go. So what happens? 74 is not in the second category, but it's in the third category. Why do you think that would be the case? Look carefully at the values. 74, 75, 76, 77, they're all the same. So in non-spatial analysis, the third quintile starts at 75. But in spatial analysis, since each of these 4 observations are in a different location, we don't know which one to pick. Which one of these 4 are we going to bump down to the second quintile? All right. So in non-spatial analysis, 37 up to 74, then from 75 on is the next one. It's all, the values are all correct. In spatial analysis, because of ties, we don't know which one to pick because each of these is in a different place. For example, if I go back to the table and I kick this one out, you do command click on this. So I'm kicking it out. If you look at the map, it's here. So I'm kicking it out. And let's say I'm, yeah. So now it's would be classified as the second quintile, but it's the same value as these ones. And these ones are here, see it? Here, here, up on the top, up here. And so which one of these you include in your map is going to give a totally different impression of the spatial distribution of the values. So that's a downside of a quantile map, even though in many mapping packages, that's kind of the default, or it's the first case that pops up. Sometimes it's good, but you can run into weird situations when you have when you have ties. One classic example of this is if you make a map of homicide rates by county in the US. There are all kinds of counties, especially in the upper Midwest, that have no homicides. And so if you do a quintile map, right? So let's say roughly there's 3,085, let's say 3,000 counties in the US. You divide that by 5. This would be 600 in the first category, 600 in the second category. If more than 600 counties have no homicides, we're in trouble because we don't know where to draw the line. Which ones are we going to put in the first category and which ones in the second category? What GeoDa does, and some other packages do this too, is it bumps them all up to the next category. So in that case, a quintile map of homicides for US counties will not have any observations in the first category. They will all be bumped up to the second category, which will now have 1,200 counties in it, or something like that. Okay. So when you make a quantile map, always look here in these parentheses how that looks. It should be roughly equal. In some instances, you may have 0 here in the bottom one. Then it's clearly not the right classification. Remember, what we're doing is putting a continuous distribution into bins, into discrete bins, just like we do with a histogram. And these bins become colors on the map. So if the distribution is weird, like it's flat and then it's only starting after a lot of zeros, then this is not a good classification. It doesn't give you a good sense of the spatial distribution of the data. Another downside of the quantile map is that even though there's an equal number of observations in each category, the size of the category is not equal. Okay? It's simply based on the ranking of observations. But the difference between the lowest ranked one and the highest ranked one in the same category is not constant across categories. In fact, if you can see it here, some of these are pretty small, like 0.79 to 0.822. But then here, it goes almost 100 difference, right? So that's a drawback of the quantile map. So good point, equal number of observations in each category. Bad point, you don't control the range. Okay. Next one, equal interval map. As the name says, equal intervals. We control the range, but now we're not going to control the number of observations in each category. So let's start by making a histogram. Histogram is part of the EDA. It's a very simple function. It gives you a quick and dirty look of the distribution of the data. So we picked the histogram, same variable, housing. In GeoDa, it always defaults to the variable that you've been using. So if you do a lot of things with the same variable, you can almost automatically click OK. You don't have to look at it. It's always the same one. The default for histograms is to have 7 categories. Now we're comparing this map to a quintile map, so we need 5 categories. We're going to change, right-click on the histogram, choose intervals. It's the first option. And we're going to change this to 5. So it's 7, that's the default. We're making it 5. Then you say OK. Then instead of having 7 bars, you'll have 5 bars. Okay. This is by no means equal, right? Each of these, if you hover over it, it can tell you what the contents are of each bin. If you go view, and then you go down display statistics. So you right-click on the histogram, view, display statistics. Then on the bottom, you see exactly what the ranges are and how many observations there are in each of these bins. You know, so 8, 21, 75, and so on. Okay. So this is a histogram. This is our non-spatial representation of the distribution of the data. Now we go into either the map menu or here, the tool bar icon, and we're going to equal intervals map, which is way down there, the next to last one, and we go down to 5. So equal intervals map, 5 categories. It's housing again, it's picked, okay, and this is our map. This is the spatial representation of the histogram. And I'm going to show something that I may have shown before, is the notion of linking. I think I showed it for the table. If you select something in one window, it's immediately selected in all the windows. So let's select the middle category in our equal intervals map. We know how to do that. We click on the little rectangle. What's going to happen in the histogram? only shows the middle bar. Okay. That's linking. If you go the other direction, you click on a bar in the histogram, it selects the observations in the map. Okay. The dynamic version of linking is called brushing. And in brushing, you select a rectangle. So click down on the map and draw a rectangle. This is selection by area. You can do it with a rectangle, you can do it with a circle, you can do it with a line. And here we take a rectangle. So let me step back a second. Why would we want to do that? This is to get at a notion, I mentioned this before, the notion of spatial heterogeneity. Not everything is the same everywhere. Specifically, the distribution of the data, everything else being the same, should be exactly the same no matter where we go in the data. Remember, we talked about this in the context of polling. If, the distribution of sentiment is exactly the same everywhere in a state, then it doesn't matter where you poll people, you always get the same result, right? But if it's not the same everywhere in the state, then depending where you are, you will get a different distribution. One way you can assess this visually in GeoDa is to brush the map. And as you brush the map, you see whether the selected distribution, the little mini histogram, follows the same pattern as the big one. In some cases, it's close enough. In other cases, it's very different. And there's much more concentration, say, of the lower values or of the higher values. So let's do this. We just move this rectangle over the map. And as you move it, the selection changes and the selection is updated in the histogram. So this is brushing. In some cases, is more or less the same, but then in other cases, if I remember correctly here, it's totally different. Yeah. So the point of departure is that it should be the same no matter which subset you pick. It should follow the overall pattern of the original distribution. If it's very different, then we have a suggestion of spatial heterogeneity. In other words, subset that you take does not have the same distribution as the set overall. I'm not going to call it the population, but you can think of it in a similar sense. If you're used to sampling, you take a subset of spatial units and they don't follow the same distribution as all of them. And that's a suggestion of spatial heterogeneity. So linking and brushing is the basic architecture underlying GeoDa. So everything is driven by linking and brushing. No matter where you go, for example, if I go here, I select on one variable. This is not the same variable. Well, actually, in this case, it is. So it doesn't really hold. But same thing, you can move around and see what happens to the distribution. You can also do this for other variables, and that gives you then a sense of interaction between two variables. But let's go back to our equal intervals. So the last one of the classic ones is called natural breaks. And the natural breaks map, all the way down here, uses an optimization approach to finding the cut points. Is the same principle as k-means clustering. You may be familiar with that. So the idea is to group observations into subsets so that within each subset, they are as similar as possible. And the subsets, therefore, are as different as possible. So what you're looking for is in the data is very clear breakpoints. And then you put them together, it's on a line, so it's not that complicated. you put them together in separate categories. So again, you pick the number of categories. We'll keep doing 5. It's the same variable. We say okay. And now we have a natural breaks map. So what I forgot to mention is equal intervals. Obviously, by construction, the intervals are equal, but the number of observations in each interval are not the same. That's the height of each of these bars. Natural breaks is yet different. For example, there's 6 in the top category. So there's 1 in here that's not included in the top category. There's 13 in the lowest category. So this one spills over into the second bar. So each of these categories is based on a specific optimization criterion. And in many cases, not always, in many cases, this is a very good type of classification to use because you let the data do the classification. So here in this case, you don't control anything. You just control the number of intervals. You don't control the range within each interval, and you don't control how many observations are in each interval. That's the result of the optimization routine. In quantile maps, you control the number of observations in each interval if there are no ties. In equal interval maps, you control the range, but not the number of observations. In natural breaks maps, you don't control either. So it's the data that drives where the cut points are made.